All right, you guys, happy Wednesday. I hope all of you are doing well. I miss seeing your sweet faces. Please continue to give me feedback on what you feel like will be the most helpful for you. I really want to make sure that I'm making adjustments so that we can be the most successful we can possibly be. So to start off, this next section of our unit, now that we are master factor labelers, we're going to start talking about how we keep track of stuff in chemistry. Atoms and molecules are really, really tiny, and there's a whole lot of them. And so we really need to think about how chemists keep track of them all. So this is the mole, and it actually has nothing to do with the tiny eyeless mammals, and we'll kind of talk about where this name comes from a little bit later. So before we start talking about moles, let's use an analogy. So we'll look at a familiar scenario that really is directly comparable to the mole. So take the example of roses. If we look at this bouquet of roses, we want to think about like how many roses are in this bouquet. We might guess that there's 12 because that's usually how many roses you get in a bouquet. We could also just count them, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there's 12 roses. What different units can we use to describe the roses in our bouquet? We can say, I have 12 roses. You could say, the roses are 340 grams. I have 340 grams of roses. Or you could be a normal person and you could say, I have 1 dozen roses, right? And we talk about dozens pretty frequently. And we know that 1 dozen is 12 things. So any substance that we have, a dozen of them is 12 of them. So if you have a dozen roses, you have 12 roses. If you have a dozen donuts, you have 12 donuts. So then we can say, all right, if we want 48 roses, how many dozens of roses should we order? All right, so I can take my 48 roses divided by 12 roses is a dozen, and that gives us, we need 4 dozen roses. That would be kind of expensive, but awesome. Okay, so we can just take our 48 divided by 12 to get 4 dozen roses. If we take this to a slightly more chemically related application, we can think about a glass of water. So how could we measure how much water is in the glass? How could we know that? And what are some of the units that we use to describe water? So a lot of times we use volume. We talk about milliliters. Sometimes we talk about fluid ounces, like, you know, my 32-ounce Nalgene. We can talk about the mass. The mass of 50 milliliters of water is about 49.9 grams, depending on the temperature and the density of the water. One can also talk about the water molecules themselves. There's 7.38 times 10 to the 23 water molecules. And if we wanted to get even more in depth, if we counted all the hydrogens and oxygens, we would have 2.22 times 10 to the 24 atoms. And that is a lot of stuff. But in chemistry land, we're really interested in those molecules and those atoms. And so sometimes we're going to have to deal with these really large numbers. And so if we want to be able to write these out, scientific notation says you're just going to move the decimal place to the right if it's a positive exponential, to the left if it's a negative exponential. So if we have 7.38 times 10 to the 23rd molecules, that results in a lot of zeros. That's like a, I don't know what she's talking about. Or we could call it 738 sextillion. I don't know the amount of zeros in a sextillion off the top of my head, but if you do, good for you. If we look at the atoms, right, we have 2 septillion, 226 sextillion. That's a lot. And it's really difficult for us to conceptualize numbers like that and to talk about them in conversation. And it's not always practical, even in scientific notation. It's not always practical to work with numbers like this. Thus, we have the mole. So what is the mole? It is not a furry critter in the land of chemistry. It is a furry critter in the land of biology. Our mole in chemistry is defined as the number of carbon atoms in exactly 12 grams of pure carbon-12. So not a mixture of carbon, right? There's multiple isotopes of carbon. The weighted average atomic mass of carbon is like 12.011 something, right? But we're just talking about pure carbon-12. Okay, so the number of atoms in exactly 12 grams of pure carbon-12. So we know the mass number of the carbon is 12. That's how many atoms is a mole. Little side note, in the 1890s, German chemist Wilhelm Ostwald formally defined this new unit, and he named it the mole from the German word Molekül, which of course means molecule. And in 1897, mole was translated to English as mole. This is why it's helpful to look at the words on the screen, because I just said like the same word 5 times. Anyway, that is part of the issue with the mole. We named it something that sounds exactly like an abbreviation of molecule, which is an entirely different thing. And we're like, yeah, that would be confusing. Great work, Wilhelm. But yeah, anyway, we call it the mole. And so it's not a molecule. It's something totally different. And if you're interested in how Wilhelm Ostwald started to figure out and define the unit, the mole, I've posted a Scientific American article. It is not necessary that you read it. However, if you're curious, you can definitely take a look at it. Okay, so now we have our mole. And in this picture on this balance, we have exactly 12.00 grams of pure carbon-12. So that's charcoal that we have in this example. And so in 12 grams of pure carbon-12, there are 6.022 times 10 to the 23rd atoms of carbon. That is a lot of atoms. So if 12 grams of carbon is 6.022 times 10 to the 23rd atoms, and 12 grams of carbon is a mole, then 6.022 times 10 to the 23rd atoms of carbon is equal to a mole of carbon. And that is where we get our definition of a mole numerically. So this definition can be generalized to apply for things other than carbon. And so 1 mole of any substance is equal to 6.022 times 10 to the 23rd units of that substance. This huge number, 6.022 times 10 to the 23rd, is called Avogadro's number, and it can be denoted capital N subscript capital A. Avogadro was an incredibly influential chemist very, very early on in the very early days of chemistry. And so this number was named in honor of him. This number is rounded. We can use a longer version of it, but typically it is common practice to use 6.022, even though there are more decimals that follow. So this is a constant, which means it never ever changes. So 1 mole is always equal to 6.022 times 10 to the 23rd. That will never not be true. Okay, so 1 mole of anything is always 6.022 times 10 to the 23rd things. That is a universal chemistry constant thingy. All right, so some examples. If you have a mole of sodium, you have 6.022 times 10 to the 23rd mole atoms of sodium. If you have a mole of dogs, you have 6.022 times 10 to the 23 dogs. If you have a mole of water, you have 6.022 times 10 to the 23 molecules of water. Also, look at all those cute dogs. I just love their little faces. Okay, anyway, moving on. So if we look back at our example of 50 milliliters of water, this unit, the mole, allows us to go from 738 sextillion molecules, or 2 septillion, 220 sextillion atoms, and it allows us to just say 1.23 moles of water. That's like, oh, okay, that's way easier to talk about. Okay, so we really want to be able to relate the mole to something that we can directly measure. We're not going to count out, 6.022 times 10 to the 23 molecules or atoms of something. And so luckily, we have this relationship between the mass of an atom and a mole of that element. So molar mass is the mass in grams of a substance in 1 mole of that substance. So that just means you have 12 grams of carbon, it's equal to 1 mole of carbon. And so 12 grams per mole equals our molar mass. So basically, it's just created a conversion factor for us to be able to get from grams of a substance to moles of a substance. And this is true for any element. Some examples include 52 grams of chromium equal 1 mole of chromium atoms. And so that tells us 52 grams per mole of chromium is the molar mass. 23.99 grams of sodium is a mole of sodium atoms. And so 23.99 grams per mole is the molar mass. Iron is exactly the same. 55.85 grams of iron is 1 mole. So 55.8 grams per mole is the molar mass. Looking at these examples, where do you think the molar mass of an element might be found? If you said the periodic table, you're right. So the periodic table has the weighted average atomic mass of an element, and because we defined a mole as being 6.022 times 10 to the 23rd atoms in the mass of an element, now we can say that the weighted average atomic mass is the molar mass. So yeah, it can be found on the periodic table. Its unit is grams per mole. That's going to be really important for us to remember. And this is super handy. For us to use. All right, so we want to know how the mole relates to something we can directly measure. And so we have some examples here using the element lithium. So we say 7 grams of lithium, I pulled that from the periodic table, is equal to 1 mole of lithium, which is equal to 6.02 times 10 to the 23rd atoms of lithium. Try using these conversion factors and your factor label skills to get from 21 grams of lithium to moles of lithium. And number 2, take 14 grams of lithium to atoms of lithium. And in number 3, find the mass of the atoms of lithium. I am going to explain the solutions in a separate video, so go ahead and try to give these a try. You may also want to try the following examples as well, and then I will post a video going over those. Thanks so much, you guys.